Over the past couple weeks, I've been playing catch-up in my functional analysis course with respect to the homework. The reason I got behind is because I was trying to prioritize research this semester, and I did not get as much research done last semester as I really wanted to. It wasn't until like maybe November of last year where I got a whiff of something that could become a paper, and I got really excited. So I prioritized doing that instead of doing my homework. And the homework problems this semester, I think, were on average more challenging than last semester. So I was kind of scared to do some of the stuff. There was one homework problem that's carried over that no one's done, carried over from last semester because no one did it. And it's a famous result. It's in the Katz-Nelson book. I read it. It takes about a section to explain. And I was going to present it. I actually did present it once, but I did not manage to explain it very well, so I was forced to come back and do it later, although I never did. The reason is because it takes like an hour to explain. It's really tough. And if you can't explain everything, then you don't get credit for it, unfortunately. So I was just going to wait for something simpler. But what ended up happening is that 15 weeks went by and I only solved like 3 homework problems. Everyone else is almost done or done at this point. And over the past 3 weeks, it's like, okay, I really do need to get this class taken care of. So I started one homework problem. It was tough. I got stuck halfway through. I asked the instructor for help. He didn't help me. And then I did another problem. Didn't get very far. Started another problem. Got about halfway, couldn't figure out how to finish, and it's just been bad. It's been rough for the past 3 weeks. I'm gonna be honest with you. So, but I did end up getting 2 homework problems that were reasonably simple, and I have written them up here. And I want to say that I solved them, or that I have the solutions here, but I'm a little bit scared of what I've written. And I actually showed my friend in the class what I had written, and he basically agreed with me. He thinks that everything I've written here works. So that's why I feel okay sharing what I've written for these 2 homework problems on YouTube. And if not, I'll fix them later. It's no big deal. I got pretty thick skin, even if people call me a moron. The moral of the story, I guess, is don't get behind on your homework, even if it is with the best intentions. You're doing your research and being a good little student. You do your homework, but do all the things that you know you should be doing in the beginning, and then focus on the stuff that you want to do, I guess is what I'm trying to say. So with that being said, I think we should get into the homework problems, because they do take not that long to explain, but if I don't start now, then this video will be like 30 minutes, and that's way too long. Okay, so the first problem is a bit strange for a functional analysis course because it's in the realm of spherical harmonics and convex geometry. When my instructor got done discussing BMO functions, he asked us what topics we wanted to discuss next, and he gave us 2 options, so we voted. One was about spherical harmonics, which won the vote, and the other was like about Hardy spaces or something. And the reason that we picked spherical harmonics is because a lot of people in the department do research in that field, and I think that it would be beneficial for us to go over it. So that's kind of why we voted for it. So this is like one of the first homework problems that was given when we started this topic, and it's kind of a benign statement if you really read it. You have this convex body K, and Rn, you have this, we can assume that the origin is contained in the interior of K. So, and moreover, I can call it the center. I can just translate the body until it centers at the origin. And we assume that the radial function rho, so rho denotes the radial function. I've mentioned it on the channel before. I don't know if I explained it very well, but we have this radial function rho, and we're saying that it's identically equal to the support function h on for vectors given to you on the unit sphere. So visually, what does this mean? What do these 2 functions do? So you have this convex body K, which is this oblong shape that I've drawn here. And you have 0, the origin, inside the interior. So that's this point here. And you pick a direction E. So E is our unit vector. And you emanate from the origin in the direction of E along this ray until eventually you hit the boundary of K. And this distance that you travel from the origin to the boundary of K, we call rho of E. So that's the radial function. So you can see here as E spins around, this is just a two-dimensional case, but you can extend it to higher dimensions. You can spin around in a circle, taking various directions E, and then you can see that this point will trace out the boundary of K. So that gives us our radial function, hence the name radial. And then we have the support function h. So what does h say? Okay, so you have this ray going in this direction, and then you look at lines or subspaces, depending on the dimension, that are orthogonal or perpendicular, if you prefer, to the ray, okay? And the idea is that you're going to take this orthogonal subspace, this line, and you're going to push it until eventually it just barely touches the boundary of K right here. So it forms a right angle here, and it just barely touches K here. So the distance that you travel from 0, or the origin, in the direction of E until you eventually get to this intersection point here, that is what's called the support function of E, or the support function of K, and you evaluate it at E, I should say. And it should be pretty obvious from the picture that h is going to be bounded below by rho, which I've written here. And the assumption is that rho and h are equal to each other, always, no matter what input that you have. So the claim is that under this assumption, K must be the Euclidean ball. Because obviously the ball, if you think about it, is going to have that property. But the problem is that you want to show that K is the only shape that has that property. Or the ball, I should say. Okay, so how do we prove it? We start with a given direction E. So E is some unit vector that we have. And we define E perp to be the orthogonal subspace with respect to E. So E points in some direction, and then you look at the subspace collection of all vectors that have this property. So the scalar product of x and E is equal to 0. Now we're going to take E perp, this orthogonal subspace, and we're going to translate it in the direction of E by some amount t. So t is a real number in this case. It's a set of all vectors of the form x plus te, where x is an E perp. And to simplify the notation, I call it ht of E. So we have that. And if we set t equal to h of E, so this is again, the support function evaluated at E, we'll actually get this line that goes here. And, you know, if we're in like three-dimensional space, then this is going to be a plane, because this is still a ray. It's a one-dimensional subspace. And then this will give me a plane. It won't be a linear subspace because subspaces have to pass through the origin, but it's a translation of that subspace in this direction. Okay, so that is ht of E. We set t equal to the support function, but we know from assumption that it's equal to the radial function, so this is an important observation. And then the next thing I want to do is I want to look at half spaces. So I want to look at the two sides of this linear subspace. The way my advisor would explain it is that H is like the surface of water, your water surface level. And then you have this body that floats in water. And if T is large enough, meaning like if T is equal to the support function, then you've basically submerged your body in this water, and that your body K is completely contained within this set, which is what I've written here. It's either contained in H plus or H minus, depending on how you want to translate T. But if T is equal to H, then I believe it's H minus, because that's, well, I mean, that's what I think it is. So we have K as a subset of H minus TE. And what else do I want to say? Probably nothing. So visually, what do I really mean? I mean that this is your water surface level, so it might be beneficial to look at it this way. This is your water surface level. This is the underwater part, and this is the space above the water level. So K is just barely underneath the water. And since K is a subset of this space, H minus TE, for any E, that means that if we intersect all of these spaces, we will carve out what K is, or at least K will be a subset of this full intersection. But if we take a minute and think about what this full intersection gives us, because the support function is equal to the radial function, we know that this set has to be the set of all vectors V, whose magnitude does not exceed rho of E min, where E min is the direction that gives us the smallest possible output for our radial function. So if K is a subset of this, then we know it's a subset of this ball, because this gives us a ball. But we know that this set has to be a subset of K, which is what I've written here. Why do we know that? It's because, again, going back to this picture, we know that the origin, is in the interior of K, which means I can put a sufficiently small ball, around the origin that's contained within the interior itself. And the idea is that I can expand this ball and make it bigger and bigger and bigger, like what I have in the picture. And the question is how big can you make this ball so that it's still contained within K? And the answer is you can give it the radius equal to rho E of E min. So you can only make it as big as the smallest possible for the radial function that you can get. So K has to contain this set as well. So we have K is a subset and K is a superset, which means that they have to be equal to each other. So K has to be a ball. I might need to check this just to make sure that I didn't get H plus and H minus mixed up, but I'm pretty sure it's H minus. I was second guessing myself there for a second, but that's how it goes. So that was the first problem I did over the weekend. The second one I did was another fairly simple problem. It's about BMO functions. The claim is that logarithm of absolute value of x is a BMO function over the set of real numbers. So I know I've talked about BMO functions on the channel before in the video called Bounded Mean Oscillation. That's what BMO stands for. Essentially what we want to do is we want to take this guy that I've written here. We want to take the supremum of this expression over all possible i's and show that that's finite. And my strategy, or the strategy I'm using here, is I want to take this expression and get a bound for it that's independent of I, so that when I take the supremum over all I, it'll still be bounded. So that's what I want to do. Okay, so we bust it up into two cases. The first thing we do is we take an arbitrary interval I. So I is going to have center x naught, and it's going to have radius epsilon. And I say radius because intervals and balls on the real number line here are going to be the same. So we have I equal to this guy. And in the first case, we look at the situation where the center, x naught, is sufficiently far away from the origin. So 0, meaning it's more than 2 epsilon away. If the value x naught is sufficiently far away from the origin, more than 2 epsilon, then the question becomes how close can x be to, well, excuse me, let me say this a different way. If we have a number x in this interval I, then what are the bounds on the absolute value of x? Well, we know that it can't be less than half of the distance of x naught from the origin, and we know that it can't be more than 3/2 absolute value x naught from the origin. So we're looking at how far x can be away from the origin in terms of x naught. And if you're struggling to understand this inequality, you can just draw a picture of it. It's once you draw, the picture's not hard to draw. In fact, I don't want to get into it too much because this video will be longer than I want it to be. But the picture explains it better than I can. Okay, so I want to make mention of that here because it comes in useful later. So the first thing I'm going to do is I'm going to pick my constant c depending upon I, and the constant that I choose is going to be the natural log of x naught. Here I wrote ln, here I wrote log. It's still the natural logarithm. I'm not really sure why I wrote ln here instead of log, but it's the same logarithm. So now we have the expression that we're interested in, and we want to get an upper bound independent of I. So the first thing I do is I can substitute in my c, and then I have log absolute value x, which I didn't write for some reason, minus natural log x naught. Use property of logarithms to write this as a single logarithm. So we get absolute value log absolute value x over absolute value x naught. And then you can substitute in what we know about x naught, or excuse me, what we know about x, because it's bounded above by this, bounded below by that. So we can substitute these guys in for here. This gives us a constant that can be pulled out. The integral will cancel with the measure of I, because the integral over I dx gives you measure of I, so they cancel. And we end up getting these two constants that show up here. And we know that either of those two constants is going to be bounded above by the maximum of the two. Whichever one's bigger is going to bound that integral. And this guy is clearly bigger than this guy. So this guy is equal to the natural log of 2. So I have a bound that's independent of I. So if I take the supremum over all I get my bound for case 1. So everything's good. Now, what about case 2? So in case 2, we have the center of our interval I is within a neighborhood of 0, specifically 2 times epsilon. So for this guy, we're going to pick a different constant. We're going to pick c is equal to the natural log of e, or the natural log of epsilon, sorry. My brain misfired there. And then we do the exact same thing. We substitute in for our constant c. This guy gets plugged in here. So we get this natural log, or absolute value natural log, absolute value x over epsilon. And the next thing we notice is that our interval I, so again, this is I, is contained within an interval of size, or excuse me, an interval of radius 3 times epsilon centered at the origin. So I make the integral bigger by making the domain of integration larger, which is appropriate here because everything that we're doing is non-negative. This integrand is non-negative. So we end up getting this expression. And I decided to substitute in what I know about the measure of I. It's going to be 2 times epsilon. And then I do a substitution. So x is just a dummy variable that shows up here and here, which if I was being more appropriate, I should have probably chose something else like set u equal to absolute value x over epsilon or something. But it's okay. So you do this substitution, you'll get this guy, and epsilon will pop out, which cancels with the epsilon in the bottom. And you'll notice that this guy is completely independent of our interval I. There's no x naught or epsilon over here. And we know that logarithm is integrable in a neighborhood of 0 because it decays exponentially when you get closer and closer to 0. So you can compute it, you'll get some number, and then that number will be independent of I. You compare it with this number that we got up here and just pick the larger of the two. So the supremum over both cases will be bounded above by some finite number. The computation I did down here, I think there's an algebra mistake, so that's why I'm trying to hide it. But I need to go through my algebra again to make sure that it's correct. But the important thing is that this guy is definitely some finite number, independent of I. So that takes care of logarithm. And this problem was a two-parter. So what I just did was part 1, and this is part 2. We want to construct a BMO function f that is not essentially bounded on any open interval. So this problem kind of scared me a little bit because I wasn't really sure how to approach it. Although whenever you're trying to do something where you want to show a function has a property that works on every open interval, or a property fails on every open interval, a lot of the times you use the rational numbers in some sense, because the rational numbers are everywhere dense, they're plentiful, and they're countable, which is really nice. So that was kind of what I started with. So what I'm about to show you here is a struggling grad student original. I pretty much came up with this all by myself, and I showed my friend it, and he thinks it works too. So what did I do? So I used the fact that BMO is a linear linear space, I should say. Meaning that if I add 2 BMO functions together, I get a BMO function. And if I scale a BMO function by some scalar alpha, then I also get a BMO function. Moreover, that if I take the sum of f and g, two BMO functions, and I take their BMO norm, then it's going to be bounded above by the norm of f, the BMO norm of f, plus the BMO norm of g. Moreover, if I take the BMO norm of alpha f, then the alpha can be pulled out, so I get absolute value alpha times the BMO norm of f. So those are just some remarks that I have that are useful. Okay, so what? I mentioned rational numbers. We take an enumeration of our rationals, which I give here, and then I define a function logarithm, absolute value x minus qn, all in absolute value. So logarithm is a BMO function. If I translate it by qn, to the left or to the right, all it does is it moves the singularity. So I just take my logarithm, you know what it looks like, and I just shift it this way or this way. Doesn't change the BMO norm. You just repeat the same argument where you work around the singularity at qn instead of 0. It's the same basic argument. And then I take absolute value of everything because I also use the fact, I didn't write it here, but if you take the absolute value of a BMO function, you get another BMO function, which is really nice. I do this because I want everything to be positive. So I have this BMO function, and then I'm going to scale it. So I think the scaling factor matters a good deal here because you want the coefficients to decay pretty fast so that when you add up these functions together, which is ultimately what I want to do, I don't have any irrational numbers that when I plug it into the function, I don't want them to escape to infinity. So I'm trying to play this game of convergence here. So I originally wrote down this coefficient because it decays pretty fast. I might swap it out for this one. I have to think about this more. Something about this scared me. So when this video is done and I post it to YouTube, I'll probably figure out which coefficient I really should be using. But the idea is that we can choose these coefficients so that they decay fast enough where if I sum them all together, so fn is equal to this guy, which is a BMO function, I can add them all together, and hopefully that gives me a BMO function. So what do I need to do to check to make sure that f is a BMO function? I want to show that f is locally integrable and has finite BMO norm. So the first thing I do here is I show that it has finite BMO norm. So I take the BMO norm of f, I substitute in the definition, sum of fn. I can use triangle inequality. So that's basically, I'm using this property to get less than equal to sum over BMO norms of fn. I substitute in what I know about the BMO norm of fn. So I get this coefficient that my alpha n's that are here, that show up here. All my coefficients are positive, so I have absolute value, but I don't need it written. And then I have BMO norm of fn. But the BMO norm of fn is equal to the BMO norm of logarithm. So it's independent of n, which means I can carry it outside of the summation. So I get BMO norm of f0, for example. I can just pick f0 if I want. And then I have this sum of this really fast decaying sequence. And I can use a variety of different tests to show that this summation converges. So it gives me some constant c, which I don't really care about, because I'll have a finite number times the BMO norm of f0, which is finite because I chose it that way. So everything here is finite. So the BMO norm of f is finite, which makes me happy. The next thing I do here is I show that my function is locally integrable. So I think in the Stein book they say that it depends. I don't know. In the Stein book I know they say that a function is locally integrable if you take that function in absolute value, multiply it by the indicator function over a ball, then that function that you get is integrable over the whole space R. So in my case, I write e here, but e is going to be some interval. Okay, so I just wanted to make mention of that. So I want to show that this integral is finite. So what do? I take absolute value of f, I substitute in the definition of f, and then I play the game of triangle inequality again. So I have absolute value summation. I can push the absolute value in, and then this coefficient is, this alpha n is positive, so I can pull it out. And then I can swap the integral with the summation here because of monotone convergence theorem. Everything here is non-negative, so I can pull it out. So I have sum integral over my interval e. I have my coefficient, logarithm x minus qn. And really, I can take this coefficient, I can pull it out over here as well. So now I want to figure out what the integral over e of log x minus qn is. And what I do is I'm going to cover e with intervals centered at the rational numbers that appear in the closure of my interval. So for the rational numbers that are in my closure, I am going to define an interval I n k to be q n k minus 1, comma, q n k plus 1. So that this at e bar, this closure of e, is e is going to be a subset of the union of all these intervals. In which case, this integral I have here is going to be bounded above by the same expression I've written here, except now I'm doing it over all intervals that cover e. So I've replaced the domain of integration with something bigger. And what I notice about this is that, okay, so I pull out my alpha n here, alpha nk, and this integral is finite, because this is basically the same as natural log absolute value x and absolute value over the interval from -2 to 2. No, sorry, that's wrong. From -1 to 1. This gives you like 2, I believe, although, just a second. Yeah, it's 2, okay. So this gives you like 2, and you can factor out the 2, and then you just have 2 times the summation of these coefficients I have here, which, you know, is that same constant that I had. Well, actually, no, it's not the same constant because I'm not using all rational numbers. But it doesn't matter. I can replace it with something larger. It's only smaller, so it has to be finite, which means that my function f is locally integrable. Okay, that was a lot. That was a lot, man. I feel like I need to refine this talk a little bit more if I'm going to present this tomorrow. If it goes well, I'll probably confirm it went well. If you don't hear back from me, it probably didn't go well. But I'm gonna go back over this tonight, make sure I don't make any mistakes. If I did make a mistake, I'll probably pin a comment in the comment section and make sure that I keep myself honest. I hope you found this informative, in which case, you're welcome. I don't know. It's been a while since I made a video. I forgot how to talk in front of a camera. So anyway, thanks for watching.